Hello, it is an honor to be called upon to present my abstract at the AMAA African Conference, Summit and Technology Showcase 2023. I am in the person of Functions Fifi Mensah, and I'll be presenting on the topic Development of a Smart Temperature Control System for a Green Dryer. In this study, the green dryer refers to a solar biomass assisted dryer. This research was conducted by myself, Pakwasisa Kadenchi, and Professor Joseph Opoankuwa. We are all from the Department of Agriculture and Biosystems Engineering at the Kwame Nkrumah University of Science and Technology in Ghana. In Ghana, grain drying is mostly done in the open using the sun's energy. Open sun drying is one of the most common methods of drying crops in Ghana, but this method of drying is vulnerable to pest, contamination, weather dependent, and also labor intensive. Smallholder farmers do not patronize the use of mechanical dryers as drying cost is often high. These dryers make use of LPG or diesel as a source of fuel. To support smallholder farmers, there has been recent development of small capacity dryers which makes use of biomass and solar energy. Figure 1 shows how open sun is done, and Figure 2 shows how field drying of maize is also done. Even though there's a solution to open sun drying and the high-cost mechanical dryers, but the solution being provided has a limitation of temperature regulation. Thus, it is very difficult to control the temperature as dealing with the biomass is concerned. Moreover, certain crops require specific temperature for drying. The temperature required for drying maize might not be the same for cocoa or cassava. The flow of hot air within the dryer is as shown in Figure 3. Recent study has shown the potential of microcontrollers being used for temperature control applications. Figure 4 also shows utilizing bamboo for drying of maize. As we all know, bamboo burns faster and has a higher calorific heat capacity. And if not controlled, the heat can cause damage to the maize. This then leads us to the main objective of this study, to develop the smart temperature control system for the biomass assisted dryer. Our specific objectives were to design and manufacture a smart temperature device to help assist the biomass solar assisted dryer and also compare the temperature sensor to a calibrated temperature data logger. Let's get to know more about the biomass solar assisted dryer. The biomass solar assisted dryer has 3 chambers, namely the combustion chamber, blower unit, and also the drying chamber. The combustion chamber is where the biomass is burnt, and the blower unit sucks the heat and directs it into the drying chamber. In this study, the temperature device will be coupled with the blower unit to help in regulating the speed and in terms the heat coming into the drying chamber. The components used in developing the smart temperature control system are below. We have the Arduino microcontroller, which in this case serves as the CPU of the circuit. This is where instructions or algorithms are stored on to function or act accordingly. The LCD display screen serves as a monitor to help display the temperature readings and also helps in setting the thresholds or temperature limits. The LM35, when the 10K resistor is connected across to it, can serve as a temperature sensor. The soldering iron will help us join the wires and also the sensors to the PVC board. We have the relay, which is an electromagnetic switch which will take instructions from the microcontroller or will be triggered by the microcontroller to turn on or off. We have the jumpers to serve as our connecting wires, and we have the push buttons to help reduce or increase the thresholds or the set points that we want. There was an application of applied electricity in this research, the rectification circuit. In powering our circuit, we needed 5 volts direct current. In doing so, we had to convert the 230 volts AC to a 12 volt DC and give it an adapter to convert it to the 5 volt direct current that we needed. We constructed this rectification circuit to convert the AC to a DC power source. In Figure 8 is the description and construction of the circuit unit. We have the 80 mega, in this case the Arduino microcontrollers microprocessor, and we also have the LM35. We also have the LCD display screen. Above is the rectification circuit unit and also the relays and the push buttons, and all the components, as you can see, is being connected to the microcontroller. The control algorithm is as shown in figure 9. The control algorithm used is called PID. PID stands for proportional, integral, and derivative. First of all, the program is start by powering the circuit, and the PID starts initializing. It first takes the initial reading or the temperature of the environment and allows you to set the set point temperature. After setting the threshold or the set point temperature and the heat starts coming in, the sensor measures the real-time temperature and compares it with the set point or threshold. When the real-time temperature exceeds the set point or threshold, it triggers the blower to stop, and after cooling down or the temperature goes below the set point or threshold, it starts the blower again. We gave it an error margin of 3, and the temperature is updated every 5 seconds. Once the crop is dried, then you turn off the circuit. The temperature device can be installed to the dryer as easy as installing a switch. The live wire of the power cable of the blower is divided into 2, and the circuit is connected across to it. And once plugged, you just set your temperature limit and you leave it to run. This was the final outcome of what we gathered together. We have the display screen, as you can see, displaying the temperature and also the set point for you. We also have the LM35 temperature sensor. We have the push buttons. We have the green button to increase the values and the red button to decrease the threshold values. We have the reset button to help you restart the whole program and also set new temperature threshold or limits. As stated in our specific objectives were to compare the temperature sensor with a standard data logger. We were able to couple the temperature data logger together with the smart temperature control system. The sensors were placed in the drying chamber and ran for a period of 200 minutes. Figure 11 shows a variation with time in minutes and also the temperature in degrees Celsius. After running it for the period of 200 minutes, we gathered the average, and the average for the data logger was 68.14 degrees Celsius, and that of the LM35 sensor was also 65.77 degrees Celsius, with a difference of 2.37 degrees Celsius. On the chart, the blue line represents the data logger and the red represents the sensor which was used. As you can see, there was a trend in it. Wherever the threshold reaches and turns off, you could see the temperature dropping. And whenever the threshold turns on, you could see it rising till it started falling. To conclude, the smart temperature control system was successfully designed and manufactured and coupled with the biomass assisted dryer. The operation was done for a period of 200 minutes where biomass was combusted and compared with the existing data logger. The developed temperature control system for the biomass assisted dryer will optimize the drying process and improve crop drying. Further studies will also be conducted to fine-tune the sensor to match perfectly with the data logger's readings. Thank you.